Okay, so let us start. So today we are going to discuss the Green's identity and Stokes theorem. So these theorems, right? So both are actually more or less similar. So it applies open surfaces. So this applies for open surfaces. So Gauss divergence theorem applies only for the closed surface. So here, if there is a closed contour, then that encloses certain area. Now, Green's theorem and Stokes theorem, so these theorems actually talks about the open surfaces, not the closed surfaces. Got it? So, as and when there is a closed contour, let us say I have a closed contour like this. Now, on this closed contour, so there is a certain region that is getting identified by this closed contour. Now, what Green's theorem states is, suppose if there is a closed contour, then let us say I have a integral f dot dr. So this is actually otherwise expressed as some function of phi of x comma y dx plus psi of x comma y dy. So this is two different functions. So here both includes x comma y. So any issue with the voice? Okay, great. Fine. So I think Deepak, you checked it once. So this is, if this is the integral and this integral on a closed contour. So the closed contour obviously it encloses a certain region. Now in this region, so this value is equivalent to double integral over the surface S. So this surface enclosed by the closed contour. Enclosed by the closed contour, right? So over the surface S, this value is equal to dou psi by dou x minus dou phi by dou y over the integral dx dy. So this is what is the Green's identity. Got it? So this talks about if there is a closed contour on a plane. So this applies on a plane. Got it? So, but this can be extended even to the 3D as well, but in our syllabus we have only on the plane. And one more, the Stokes theorem, what it says is, suppose if there is a function f dot dr, so f is the vector function or the vector field, and then for this particular vector on a closed contour C, this value is equal to double integral del cross f dot n cap ds. This is over the surface S. So this is again the surface which is enclosed by this closed contour. Got it or not? So here actually for Green's theorem the condition is obviously so phi psi dou psi by dou x and dou phi by dou y. So should be a continuous functions. Should be continuous. So this is most obvious. Got it? So these are the two important theorems which talks about a closed contour. In Gauss divergence theorem, we are talking about a closed surface which encloses certain volume. Here a closed contour which encloses certain region or certain surface. Right? So that is the difference. Got it? So I just want to repeat. See this. So Green's theorem and Stokes theorem. So these two are actually applicable for a closed contour. A closed contour okay. See this. So closed surface means, suppose imagine a room. So a room actually a closed surface, which means it involves 6 different subsurfaces. So this wall, that opposite wall, left side and right side, and top and bottom. So all the 6 different surfaces enclose a certain volume. So all these surfaces together we call as a single surface called a closed surface. Now obviously within this particular room there is certain volume of air. So that means a closed surface will enclose certain volume. This is one understanding. So this understanding is applicable for the Gauss divergence theorem, right? In case of open surface, we mean here a closed contour. Let us say there is a ball. The ball got cut in certain manner. Now obviously if you look at from the top where you have cut, so let us say this is a ball, then I have given a cut like this. Then if I look at from this side after removing this, what is the kind of shape I am going to see? If I look at from this side, what is the kind of shape? This is a ball, I just cut like this. It will be a circle, right? So this circular surface, if I put it here, this will be like this. So this is the closed contour. And this closed contour, right? So this is binding this particular surface. Got it? So these are the limits. This circle is the limit for this particular surface. Now it is an open surface. So from top actually you can see this, whatever is there inside. So that's why this is an open surface. So in case of Stokes theorem, this is the closed contour we can see, and this is the surface we are talking about. Got it? Okay. But in case of divergence theorem, so this is completely closed ball. Within this there is certain volume. So that is the difference. Got it? So in case of Green's theorem, so we talk about the planar surfaces itself. Suppose a circle is a closed contour which encloses a region on the xy plane. Now on the xy plane for this particular region, so this theorem is applicable. So in case of Stokes theorem, suppose if there is a closed surface, for that closed surface, if you just cut it, then you can see a open surface there. So that open surface encloses certain contour. So that contour will bind the surface. That contour integral, so integral over the contour C, f dot dr is equal to del cross f n cap ds, where ds is the surface that enclosed by the closed contour, where contour is a closed line. So this line integral and the surface integral, these two are getting equated together. So Stokes theorem equates line integral and surface integral. And surface integrals. And divergence theorem equates closed surface integral to volume integral. So this is divergence theorem. Green's theorem also more or less similar to this Stokes theorem only. So this is also one form of the line integral, and this is again the surface integral. So here actually both are getting multiplied. This talks about the region, this talks about a 3D surface got cut in some manner. That is the difference. So this is Green's theorem is applicable for the planar surfaces. So if there is a circle, so that is a closed surface. Got it? A closed contour. Understood? Do you have any questions on this? Okay. So now let us see. Again, Deepak, see, I just summarized, see this. So there are 3 different theorems in vector calculus. For all the three theorems, the fundamentals that are needed are to find out the gradient, the divergence, and the curl. So these are the three important fundamental quantities which you should be able to evaluate for a vector field or a scalar field. Got it? So this is one important understanding. And then the other important understanding is how to find out a line integral, a surface integral, a volume integral. This is another component of the analysis. And then the third component is application of this knowledge, whatever you have acquired, so to the fundamental theorems. Like there are three different theorems in vector calculus. One is the Green's identity, and the another one is the Gauss divergence theorem, and that is the Stokes theorem. So Green's identity talks about a planar surface. So if there is a planar surface that is enclosed by a closed contour, let us say a simple case which is nothing but a closed contour is a circle. So this circle equation, let us say x square plus y square is equal to a square. Now this is a circle. In other words, I call this circle as a closed contour C, because wherever we start, so there you are ending it again. This is what we call as a closed contour. Now on a closed contour which is on a planar surface, so Green's identity, what it says is, if there is a function, so let us say phi of x comma y dx plus psi of x comma y dy. So this integral, which is nothing but a line integral, so this is as if like written as phi I plus psi j dot dx into I plus dy into j. So this is the otherwise written in this particular format. So this is nothing but a line integral, but this line integral is on a plane, so involves only x and y. So no z in this, right? So Green's theorem, so here actually in our specific case, so Green's theorem actually at this particular level we have only on the planar surface. So this is a planar surface where it is a closed contour. On this, so I component and j components are there. There are no z components. Got it? So or else actually x component and z component may be there, no y component. So that is the kind of surface that actually he is going to give it. So this is the Green's theorem. This value is equivalent to double integral over the surface S, and this surface S here dou psi by dou x minus dou phi by dou y into dx dy. So these two are equivalent as per the Green's identity. Here this S is this closed contour. So this closed contour, obviously it encloses certain area. So because this is a closed contour, so on this area, if you do the area integral for this dou psi by dou x minus dou phi by dou y, so this value and this value are one and the same. This is what we call as the Green's identity. Got it? And the Stokes theorem, what it talks about is, suppose if there is a 3D surface, let us say ball, on the 3D surface, now if you cut one side, suppose I have cut this 3D surface like this, now I have removed this particular part. Now obviously if I look at from this side, I am going to see a circle like this, and this circle is a closed contour. This is a closed contour bounding area, obviously, right? So this is the surface area we are talking about. Now this surface area is bounded by the limit of this closed contour C, which is nothing but a circle in this case. Now for this kind of cases, we have something called the Stokes theorem. What it talks about is integral f dot dr is equal to double integral over the surface S. So this is the surface now we are talking about. So for this particular surface, so del cross F dot n cap ds. Got it? So these two are equivalent. Again, this is a closed contour. The corresponding surface, this is enclosed. So Stokes theorem equates line integral to the surface integral. Divergence theorem equates surface integral to the volume integral. So that is the serial way. Got it? But quote and unquote, what you need to understand is line integral is equated to surface integral by Stokes theorem, but this is a open surface. So this is not a closed surface. It's a closed contour open surface. But divergence theorem talks about closed surface which encloses volume. So there is nothing like a contour there. Got it or not? So hope you understood. This is simple understanding. So now let us see some problems based on this understanding. That is, verify Green's theorem. Verify Green's theorem for integral over the contour C xy plus y square into dx, xy plus y square into dx plus x square into dy where C is bounded by y is equal to x and y is equal to x square, where C is bounded by y is equal to x and y is equal to x square. So here there are two different lines he has given. One is y is equal to x line, so this is y is equal to x line, and another is y is equal to x square line, so this is y is equal to x square line. So this is the area that it encloses. Obviously here actually there is a line integral on this and then corresponding surface integral also is there, right? Now we are identifying the Green's theorem on this. See this. So this is xy plus y square dx plus x square dy. So for that actually what Green's theorem talks about is, so this value is phi of x comma y and this is psi of x comma y. Now as per Green's theorem, so this value, so integral xy plus y square into dx plus integral plus x square dy, and this value is equal to double integral over the surface S. So this is dou by dou x of x square minus dou by dou y of xy plus y square. So for this dx dy. So these two should be equal. That's what he states. Now here this is 2x minus x plus 2y integral over the surface S. So this is for dx dy, and this integral double integral over the surface S, so 2x minus x is x minus 2y dx dy. Now this S is nothing but that area, right? So this value, S value, so the intersection point here it is x is equal to y is 1 and x square is equal to y is another one. It implies if you solve it, so x is equal to x square, so x square minus x equal to 0, x into x minus 1 equal to 0, x equal to 0 and x is equal to 1. Correspondingly y is equal to 0 and y is equal to 1. So this point is 0 comma 0 and this point is 1 comma 1. Now if you apply the limits, x varying from 0 to 1, y varying from this curve y is equal to x square and this curve y is equal to x. So y varying from x square to x. Now if you integrate this, this is, so xy minus y square, upper limit is x and lower limit is x square dx, integral 0 to 1. So this is, so upper limit if you substitute x square minus x square is 0, then minus integral 0 to 1, and then x square if you substitute it, this is x cube minus x power 4 dx. So this is minus of x power 4 by 4 minus x power 5 by 5. Upper limit is 1, lower limit is 0. So 1 by 4 minus 1 by 5. So that is going to be 1 by 20 minus of that. So this is minus 1 by 20. That is the surface integral value. Got it? Now, so this is the surface integral value. So for this, can you find out the line integral value also and verify if you are getting the same value, minus 1 by 20? So if you want to find out the line integral, so this line actually, there are two different lines. One is this line and another is this line. So this line is y is equal to x square, or dy is equal to 2x into dx. This is one part, and here dy is equal to dx and x is equal to y. So these are the two different contours. Now actually if you apply on this, this value is going to be integral over the contour C. This value xy plus y square. Now I take the first line, so y is equal to x square line. Then it is going to be x into x square plus x square whole square into dx plus, so this is x square and dy is 2x dx. So everything is changed in terms of x. Now this closed contour, yeah. So this is for the line number 1. So this value is going to be, so integral 0 to 1 x cube plus x power 4 plus 2x cube dx. So this is 3x cube plus x power 4 dx, and the limits are 0 to 1. So this is 3x power 4 by 4 plus x power 5 by 5. So 1, 0. So this value is going to be 15 plus 4. So this is 19 by 20. So 19 by 20 is the line integral value over the line 1. So this I call as line 1. And on line 2, this integral is going to be on line 2. So this is on line 1. So line 2, this value is going to be integral. So x into, so y is equal to x is the other line. So if I make it, this is again x plus x square, and then dx plus x square dy also equal to dx, and the limits are 1 to 0. So this is, you went this way on the line, you came back on this line back. So that is 1 to 0. So this is going to be x square. So x square plus x square is 2x square plus x square is 3x square dx, integral 1 to 0. So this is 3x cube by 3. This is x cube. Upper limit is 0 and lower limit is 1. So this is 0 minus 1, which is equal to minus 1. So the sum of the integrals, so L1 plus L2 integrals is going to be 19 by 20 minus 1. So this is equal to minus 1 by 20. So as per the Stokes, as per the Green's theorem, both are coming out to be same. Got it? Understood? So hence Green's theorem is verified. What is the application of this? So this is actually, sometimes it is very tough to solve this kind of line integrals. So that can be easily solved with the help of surface integrals. So that's the reason actually we use this. Got it? So finding out this line integrals is applicable in finding out the circulation of a fluid, right? So how effectively the circulation is happening. So in a curly flow. So such kind of things actually you have to find out the curl, or actually you have to find out the line integrals. These line integrals, with the help of surface integrals, you will be able to find out easily. Got it? Noted down? So note down on problem on Stokes theorem. Verify Stokes theorem. Verify Stokes theorem for f equal to x square plus y square into I minus 2xyj. For f equal to x square plus y square into I minus 2xy into j. Taken around the rectangle bounded by the lines taken around the rectangle bounded by the limits x is equal to plus or minus a, y is equal to 0, y is equal to b. X is equal to plus or minus a, y is equal to 0 and y is equal to b. So for this particular region, so which identifies a closed contour. So for this contour, this integral value needs to be verified for Stokes theorem. Can you solve this? So this is plus a, this is minus a, this is 0 and this is b. So this point is 0 comma b and this point is a comma 0, this point is minus a comma 0. So this is a closed contour. So for this closed contour, can you verify the Stokes theorem? Anybody got it? Now let us find out the surface integral first. So what Stokes theorem talks about is integral over the closed contour C, f dot dr value. So this is equal to double integral over the surface S. So del cross f dot n cap ds. So if you want to find out the surface integral, you have to calculate del cross f first. So del cross f is nothing but I j k, dou by dou x, dou by dou y, dou by dou z, and then correspondingly x square plus y square and minus 2xy 0. So this del cross f value is coming out to be I times of, so this is 0 minus dou by dou z of this is again 0, and then minus j times of, so these two will go out, then this is 0 minus this is also 0 plus k times of, so this value is, so this is minus 2y and then this is 2y. So this is minus 4yk, k cap. So this is the curl value. Now del cross f over n cap ds, so double integral. So the area limits are, this is the area where this closed contour is enclosing. So this area limits are x varying from minus a to plus a and y varying from 0 to b, and del cross f value is coming out to be minus 4yk dot n cap is nothing but the outward normal. This is where the confusion comes, right? In case of Stokes theorem, the confusion is the outward normal in which direction we have to take it. So For an anti-clockwise rotation, usually you have to treat this as the positive z value is nothing but the outward normal if an anti-clockwise directional contour integral is there. If it is a clockwise, then actually it is going to be the inside contour integral, which is nothing but inside the normal you have to take it. It means here actually in this particular case, this is in the anti-clockwise direction. So the normal is going to be outward normal, which is nothing but k ds. So this ds is dx dy because this is on the plane. Now k dot k is 1. So if you take it minus 4 integral, so y is nothing but y square by 2. So this is integral minus a to a. So y square by 2 and the upper limit is b and lower limit is 0. So this is going to be, so minus 4 times of b square by 2 and then, so integral dx, this is x and the upper limit is a, lower limit is minus a. So this is 2a minus 4b square by 2 into 2a. So 2 will cancel, minus 4ab square. So this is the surface integral. Got it? Minus 4ab square. So once you find out the surface integral, we have to calculate the line integral value on all the 4 different lines. Now, so can you find out the line integral? So this is, I call this as A, and this is B, and this is C, and this is D. So AB, BC, CD, DA. So on these lines actually we have to find out the line integral value. I hope it is noted down. Okay, so let us find out the line integral. So this line integral is divided into line integral over AB plus line integral over BC plus line integral over CD and then DA. Got it? So then integral over the contour C. So this is line AB. So line AB is varying from minus A to plus A. So this is AB line. Now f dot dr. So f is x square plus y square into I minus 2xy into j. So dx into I plus dy into j. So this is this value is going to be, so x square plus y square into dx minus 2xy into dy. So integral minus a to plus a. Now here this is line AB. So for this line AB, obviously there will be a change in the value of x, but there won't be a change in the value of y. So hence, so this is, so dy equal to 0 and y equal to 0. So because the line is at y is equal to 0 and the dy value, there is no change along the line AB. So dy is equal to 0. This will be 0. And then y also, if you keep it 0, this value is going to be integral minus a to a. This is x square dx. So this is x cube by 3. Then a minus a. So this is, so a cube by 3 2 times, 2a cube by 3. So this is along AB, 2a cube by 3. Similarly, if you find out the line integral along BC, so this is, I hope it is noted down, I am erasing. So along BC, this is going to be, so f dot dr is x square plus y square into dx minus 2xy into dy. So along BC, so y is varying and x actually is at x is equal to a and dx is equal to 0 because there is no change along the x direction for the line BC. So y is changing, hence dy can't be 0. Obviously, if you make this to be 0, this is going to be integral minus 2x, x is a. So 2a into y dy. So the limits are y is varying from 0 to b. So this is minus 2a into y square by 2. Upper limit is b, lower limit is 0. This is minus 2a into b square by 2. So 2 will cancel, minus a b square. So this value is minus a b square. Similarly, line along CD. So CD is x square plus y square into dx minus 2xy dy. Now this is, the line is at y is equal to b. So y is equal to b and dy there is no change, and x limits are varying from plus a to minus a. So this is plus a to minus a, and then dy is coming out to be 0, and then y value is coming out to be b, then x square plus b square dx. So this is x cube by 3 plus b square x. Upper limit is minus a and lower limit is a. So this is minus a cube by 3 minus ab square minus, so a cube by 3 minus plus a b square. So this is minus 2a cube by 3 minus 2ab square. So this is minus 2a cube by 3 minus ab square. And similarly, the third line, so the fourth line integral. So the last line integral is going to be integral f dot dr, integral over the contour CD or dA. dA, this is x square plus y square into dx minus 2xy into dy. Now on this line of dA, the limits are y varying from b to 0 and the value of x is coming out to be minus a and dx value is no change. So dx is equal to 0. So this is going to be x is varying from, y is varying from b to 0, and then minus 2 into x value is minus a and then y dy. So this is 2a you can take out, and then y square by 2. So upper limit is 0 and lower limit is b. So this is minus 2a b square. Got it? So if you add all the integrals, yeah, so you add all the integrals, so these values are coming out to be, so one is 2a cube by 3 minus ab square minus 2a cube by 3 minus ab square, and then this last integral is coming out to be minus 2ab square. Yeah, so 2a cube by 3, 2a cube by 3 will cancel out. This is minus 4ab square. So hence Stokes theorem is proved. Got it? Any questions on this? Any questions on this? Okay, so with this I would like to stop the class for today. So I'm going to give an assignment on this tomorrow. So let us see how many of you are able to solve it. So in case if anybody not able to solve it, I'm going to solve it in the tomorrow's class. I will give you the assignment in the morning itself. Clockwise and anti-clockwise direction. See this. When we are taking the outward normal, here actually when we find out the surface integral, right? So the surface integral value we have taken as the outward normal, right? So because del cross f dot n cap ds. So that n cap is what? So n cap is nothing but the outward normal. So the outward normal, the standard convention we take it is, if it is clockwise rotation line integral, if you take it, then the outward normal will be outward from the line. So I think everybody is part of the group, right? So I have given, so in the mail you can check the link. So there is a group, so or you can text me on a telegram, I will add you to that group, Deepak. Okay, so the outward normal actually, if it is taken as an anti-clockwise direction line integral, the normal you have to take as the out. Suppose if you take the clockwise direction of the line integral, then the normal has to be taken inside. That is the standard convention. Got it, Mohammed? Okay, yeah. Okay, so that's all for today. So I'm going to give an assignment on this in the telegram. Yeah, so thank you. Good night. So I think, so there are some parts actually still I need to cover as part of vector calculus. So I think Serret-Frenet formulas are there. So those are important. So that we have to cover it. Once I am done with this, then only we can think of the next topic.